view of 7. Right? I'll do it up in blocks and it is mathematics here. And then I picked another one here. Oh, it looks like I'm doing node or mesh on this one. This one is a Thevenin phasor circuit. And the whole point here is to remind you that phasor circuits are not any different than any other circuit. It's just that now you've got to deal with the mathematics. And the sad thing about it is that we're not going to step back and try to interpret what's going on. I'm just trying to get those EEs to have the mathematics. Because that's more of the challenge. And then the next semester, they move on to us. So what am I going to do? I'm going to give you a head start on these problems. Right? I'm going to give you a head start. So just to let you know here, you don't have to draw these guys out because here's the exact same thing that's online. You know, and I think the final has easier problems than these, I believe. Okay? And that's set up on purpose that way.
Back around after the first phase problem.
We're on clean that part. I just want to make sure.
Okay, so I'll give you 5 minutes. Okay, I'll give you 5 minutes. Now, if you note also, just one other thing that you should note here, I think that every circuit that I give you I'm trying to set it up so that these numbers are all really nice numbers. I mean, I numbered the resistors here, but not that they're all 1K. So I can put everything to 1. So that means that the calculations should move very quickly when you do them. But it's not about the numbers, it's about the process that I'm after.
Always staying lit, dog.
Too tired to do that.
You tired right now? Good, you go out? You watch it?
I mean, I was planning yesterday. I kind of like 4 hours.
You go to that place, dude. That place is really cool.
Thank you, man.
You guys ready? I was gonna say Pacific Rim, like the movie, but then like a 6-2.
I mean, I was a while ago. I'm not stressing.
I still have some movie.
I just do them in twos. Or you can say that's 3 more numbers.
Bless you.
Yeah, oh yeah, so we do get, or we can just do. Yeah, we do. I really love it that you guys keep sitting in the same spots even though there's no goddamn moving. I just find that very
On the bottom right on horizontal, I think you have an extra resistor. Oh, damn. Is it alive? Yeah. Right. Just throws them off the balcony. Not anymore.
There's so much effort, one half and one half.
Glass on. Wonder when you were.
Didn't feel like getting up.
Every day. Did or did?
You guys, I'm home over there. One half.
Yeah, you found it correct.
Side, so you got 1/3. Okay, shall we do this? Here we go. The most important thing here is to make sure that we do those nodes, right? Think about the whole exam. Whether you're doing, you know, the second order circuit or even the op amp, draw on the damn nodes, right? If you're having trouble, draw on the nodes, and I think that's a good thing. So let's draw the nodes. So all of the resistors are one thing, right? We agreed that all resistors are 1 kilo ohm. Which then implies when I look at the units of current, it's got to be milliamperes. So here we go. So if I start to draw these, I'm just going to go, there's one node. All right, let's call that A, just to be nice. And then if I look at B, another node, maybe I call that B. And then this guy I'm going to call C here. That seems like good notation. So then I'm just going to go through it. I just want that current there. So the first thing that I see here is that since I started with A, I'll start with A. So I'll go A and B. So if I look at that, note that this, and this are all parallel. Okay? So what I'm going to do here is that I'm going to take this 10-volt source, and then I'm going to write these three as one resistor. So what I'm seeing here, so between A and B, I have this guy right here. So note that because they're all the same resistor values, I should have 1/3. Right? They're all in parallel. So if they're all in parallel, I should have one resistor that represents 1/3 of a kilo. Typically, I would have written 1/3. So just between A and B, this is what I get. Right? That's what I get. So now, let's look at the other one. So now let's focus on BC here. When I look at BC, note that BC only has these two resistors, so that has to be half a kilo ohm. But how is BC connected to AB? Well, note that they only have one node between them, so they have to be in series. So this whole block must be in series with these two right here. You with me so far? Right? Things in series have only one node. Things in parallel have two nodes. Two nodes, one node between these two means that that must be in series. So then I'm going to come in here, and I'm going to say that from here, I'm going to get one resistor that's half a kilo ohm. So in this situation here, this is between, what did I say, BC? Okay. So now I have the connection between AC. Now note, when I look at the connection between AC, note that I don't consider these anymore, right? I already dealt with AB. When I look at BC, I don't consider these resistors anymore, because I already dealt with them. So the only thing I got to deal with is what's left. And the only thing that's left is this resistor and that resistor. So we ask the question, the resistors AC, are they in parallel to A? No. Are they in parallel to BC? No, because we already saw what was parallel. So that means then that these two resistors in AC must be in series with B or must be in series with A. However you view it, so then I would come over here and note I'm going to combine these two resistors. So when I look at these two resistors, I should have one resistor, right? It's got to be in series with that. It's got to be in series with this because there's only one node connecting them, right? When I look at BC, you'll see that the key node here is C. When I look at AC, C is a special node, so therefore they only have one common node. So this has to be half a kilo. Okay? So the issue here is what is the direction of current here? Well, this guy tells me that the current is going up. And you can automatically see here with this voltage source, the current is coming down. So I better get a negative sign at the end. So I gotta put that negative sign in by hand. So what am I saying? I'm gonna say this is I. Yeah, I'm not sure to label these resistors. Where did I label that resistor as? 6. So this is 6 and 7. So then this current here has to be the current of 6, 7. But note, 6, 7 current is what? Parallel resistors. So when I look at this current right here, so just to focus on this, what this means here is that I have two resistors like this. This is 6, this is 7, and we're interested in what? That current right there. Now note, I don't know if that was rough. I don't know if you were able to follow that, but note that I had the same kind of thinking, right? Two blocks are in parallel. If there's two nodes between them. And note, I relied on that very heavily. And series means that I have what? One node. So in these complicated circuits, you want to make sure that you're just paying attention to them. So now, all I got to do is I just got to solve for that current. How am I going to get that current? I'm going to use voltage divider. Okay? So there's lots of ways that you can do this. Now remember, source transformations are not okay. I'll give you 0 if you do that, even if it is a final. So if you'll do this here, so I'm gonna just sort of like clean this up. Well, you don't have to, well, do we have to clean it up? Let's see. These two guys in series, and that's 10 volts, so each has to get 5 volts. So if I look at this here, just by VDR, we see that the voltage across this guy must be 5 volts. Even though the current, so look, they have the same voltage. They have the same voltage, they have to have the same current. So therefore, we could then say that the current of 7 has to be 1 volt, 5 divided by 1K, which gives me 5 milliamps. But of course, we have to give it a minus sign by hand to include that, so there's that. Let's do problem 2. So problem 2 here has what? Gives you a node and a mesh problem. So we have this circuit. So look, all resistors again are 1K. So, so the difference between node and mesh is almost 0, right? There's no inverses or anything. So what you want to do here is that you typically want to pick which one's the best one for you, because that means that if you're better at mesh, do mesh. If you're better at node, do node, right? And ultimately what we're interested in is that we want to find the power here. So this guy is VB, this guy's IA, and then this guy's 4A, this is 2VB, and that's that. So all we want here is we want to calculate what's the power of the 2VB source. Right? That's ultimately what we're asking. Let me give you a head start. Okay? Let me give you a head start.
Find out what the PV was. I do mesh. We would find it. We would find out. Yeah. Right. And then with that, we know what that loop is. So we already put it at the kind of condition for DC. Get the loop current there. Can you go with that too easily? I know. You're gonna go to the I forgot one. There's PED, I figured it out.
No, we don't know yet. It would be minus they've got
Of course, right. You're gonna put out a bunch of equations, right?
When I'm doing an equation for A, instead of equal to them, there's no L like I'm random equation for this. That's worse again, so I can just forget to add or subtract it. I can't.
I mean, what you're doing, the other measure. No? That'd be a super note, right?
Yeah.
That has to be this one, B plus. All
The current sources it's possible.
So I'm just wondering if I plus I plus I2 minus 1 right? Yes. Cool.
That's me every day.
And it also helps us just roll classes with this one. When you're subtracting,
Hey, so let's look at this question here. So the question is it better to use mesh or is it better to use node? Let's do the counting for both. And then let's see. Just by thinking about this, I think I would use node right away. Why? I think node just has a slight advantage. Not very much, but remember, it doesn't really matter. Well, let's do the counting for mesh. If I do the counting for mesh, I got 1, 2, 3, 4, 5 loops. 5 loops minus 2 gives me 3 loops. Okay? So in the end, I gotta have 3 loops. And then I say, are any of these current sources are they super loops? The answer is yes. This guy and that guy. So I have 2 super conditions. So I have 2 super conditions. Are there any dependent sources? Yes, that one and that one. Can I reduce the dependent conditions? The answer is no. So then I have 2 dependent conditions, and in this process here, right, the dependent condition will be that guy and that guy. So in order for me to get this, well, actually, if I get this voltage, then I'll have that current right there. So I'm seeing 7 equations. Okay. What about node? So with node here, it doesn't really matter where I put the ground at, because I'm going to get a supernode no matter what. So I probably put my ground right here. So if I put my ground right here, then that node is known. So I got, there's only 2 nodes, right? No, I got a supernode here. And then the one in the middle right here. So I only have 2 nodes. Granted, one is a supernode, right? So I get one super condition. So I get one super condition, and then, oh, check this out. See that guy? I'm going to make that node VB. So I only have one dependent condition. So I have one DC. Oh no, that's okay. I got to get that current through here. So that means that current, I'm going to have a solver. So if you look at this, this is 5 equations. Right, 5 equations. So the question is one method better than the other? Well, 7 and 5, does it really matter how many you're entering at this point? So just go with your strength. I think I'll use node. Okay? So I would then solve with node. So now let's get real. Let me see if do I agree with my notes? Yeah, I do. So here, let's check it out. So what am I going to do? So I'm going to come in, I'm going to color these guys as always, as before. I know that this node here must be what? 20 volts. This node right here, I already going to define as VB. And then I have a supernode. And the supernode here, you'll see that, how about if I call this V1? This node here, and I'm going to bring this all the way down just to make sure that we're clear here, is that, and then of course everything at the bottom is correct. So here's my 2 nodes here, right? I got my supernode. And then I have that node right there. So let's do with the counting here. So the counting here is that we have 2 nodes. One is a regular node, and that regular node is what we call VB. And then I have a supernode, and that's going to involve V1 and V2, but associated with the supernode has to be a supercondition between V1 and V2. Okay? So that's exactly where we're at. And then the DC, we only need 1 because we already took care of VB. So I need IA. So how do I define IA? Well, look at the direction of the current. It's flowing from a high to a low potential here. So it's got to be V2 minus VB gives me IA. So then I have one dependent condition, and that has to be with IA. And then I need a solver here. The solver that I need here is that I need the current. I don't know which direction of the current. Do you want to choose the current this way or that way? It doesn't matter. So if I choose, since Carl told us which direction to go, we're going to go this way. And how about if I call this guy, I don't know, I1? I'll call that I1. And so now I need a solver here for current I1. Okay? So if you look at this guy here, I have 5 equations, 5 unknowns. And just to be clear, I like to be very systematic about this. So if you have too many variables and not enough equations, obviously you made a mistake and you want to go back. So then I'm going to count these here. So I got V1, V2, VB, here's my three voltages. And then I got IA and I1. So let's write that up now. So here we go. So then I'm going to do the supernode first between V1 and V2. So if I do that, then that means I count here, so I got 1 plus 1. I'm going to keep writing 1 plus 1 just to remind you that we're doing node here. Right? 1 plus 1. So then I have times V1 minus the mutuals, which will be VB and 20. So it's going to be minus VB minus 20 volts. This is V1 node. And then if I look at the second node, this guy here, I got 1, 2. So I'm going to get 1, 1. Then I have V2. Then I have this guy with the ground, which is 0. Then I have this guy here, which is connected to VB. And any current sources? The answer is, do I have a current source speaking to supernode? This guy right here, right? So then, on this side, I'm going to get plus 5 here. Now, if I was solving this, there's no way in hell I would have written it this way. I would have said 2V1 minus VB. I would have brought this guy to the other side, I would have been 2VB like that. Right, so the first time I would have written this, I'm only doing this as a review here, I would have written it like this. That's the way I would have written it like this. Okay, I would have reorganized this in some matrix form here, but I would have I wouldn't have probably have done this in one step, but you could. Okay, so then if I look at my supercondition between V1 and V2, you can see that this is the high and that's the low, so it should be V1 minus V2. 2 VBs on the other side, so what am I going to do? I'm going to bring it back to this side and set that equal to 0. So then I go in and I'm going to look at my dependent condition. So my DC for IA, so if I look at IA here, it's this current, and we already talked about this, so this should be V2 minus VB equals IA. So what am I going to do with the IA? I'm going to bring it to the other side. So this should be V2 minus V1. Remember, it's on the other side. I bring it to the other side and I get negative IA equal to 0.
VB instead of V1.
Oh, yes, thank you for the correction. And then finally, I have a solver for IA. And I can pick any node I want. I could have picked this node. That would have been okay. But the problem is that I would have had to figure out that current right there, which means it's got to be the sum of these two currents. So I picked that node because there's only 2 really nodes connected to that. So when I look at that current IA, or I1 has to be what? I'm going to assume that this current is going that way and that current is going this way. So when I'm looking at this node right here, I'm saying that this is I1, and then I'm going to pick my currents coming in like that. So the sum of these two has to equal that. So here I go. So what's this node? Okay, so this has to be VB minus V1 divided by 1 is the VB minus V1. Plus the second current, which is this current, that has to be 20 minus V1 divided by 1 gives me 20 minus V1. So here's my equation right here. So what am I going to do? Right? Matrix magic. Should I write them out or should I just write give the solution? Solution, right? Good. Okay. If we're all in agreement, we get this matrix and we get the solutions of VB is plus 469 volts. And I get I,
Missing node VB? Is he missing node VB?
That it is.
Hey Carlos,
yes,
are you missing node VB?
no,
No.
because,
Here you go.
oh damn.
Yeah.
I meant to put it right here. Thank you for that. So I'm gonna put this down here. I am missing node VB. So if I look at node VB here, I have 1, 2, 3. So I should get what? That's what I'm gonna do. 3 VB. Then I have 2 mutuals. That guy and that guy. Obviously this is on the ground, so I got minus V1, minus V2. So then I'm gonna write V1, V2. Then you put sources into the node? Yes, there's 4IA. So note that that's supplying it, but if I bring it back to the other direction, I'm going to get a minus sign. So then I'm going to write minus 4IA equals to 0. So if I do that, so if I do that, then I get the current I1. Okay, I have different notation. I think it's 1.88 milliamps. So then the power of the 2VB must be the current I1 times VB. So you can see that when I multiply these guys two, I'm going to get a positive sign. Positive sign gives me 17.6 milliwatts. So if I look at this, a positive sign means what? That it is passive. So that power supply is absorbing power from the circuit. Any questions? Okay, let's go to the next one. Okay, everybody's favorite problem from the exam. The op-amp problem. Okay, I'm going to erase problem 1, then we'll start on problem 2.
Hey Carly,
Yes, sir.
aside from knowing what's going on behind the picture, basically, does the polarity of the op amp change the way that we approach these problems?
No. I have a positive.